That's all good. So I will not talk about my day job today, but rather I will talk about a more general problem that arises when we are trying to improve weather and climate models with machine learning. And so I want to start out by bringing everyone on the same page about what the problem is that we're trying to solve. So climate models continue to have large uncertainties in quantities that we really care about. So for example, there is a huge uncertainty still about how much warmer it will get as a response to increases in greenhouse gas concentrations. And so of course, this is something we really would like to know better. And the question is, why are there such big uncertainties between the climate models? And people have looked into this. And to figure out where these uncertainties are, we need to understand a little bit more how a climate model works. So traditionally, a climate model consists of two big components. So first, you have basically a fluid flow problem. You have the large scale dynamics, and you try to solve these Navier-Stokes equations on a grid. Now, because this is very expensive, you're limited to the grid resolution you can use. And so for current climate models, the grid resolution tends to be around 50 to 100 kilometers. Now, if we think about, what happens below these 1,500 kilometers, and I just drew a sort of imaginary box over this picture of clouds, we can see that a lot happens below this grid scale. And so most of these clouds are smaller than 50 kilometers. You can see how radiation interacts with the clouds and so forth. And the problem is, of course, now that we cannot actually represent all of these processes that are really important on our climate model grid. So they essentially fall through the grid. Now, we cannot ignore them either because they have a huge effect on our climate statistics. So what we do is we try to come up with approximations of these processes. And these approximations we call parameterization. And all parameterizations together, so typically you'll have a separate parameterization for clouds and then one for radiation and so forth, we call it physics. And so a climate model then consists of these two components, one of the grid scale dynamics and then the unresolved physics. They interact in a model time step. Now, people have looked into why we have these uncertainties, and they really pinpointed down that it is the parameterization of clouds that causes a large chunk of these uncertainties. Now, you can appreciate why clouds would be so hard to approximate. If you just look at this image, all of this nonlinear complexity, and so we really struggle in there, even though cloud parameterizations have more and more sort of realistic, they keep having a large uncertainty. Now, ideally, what we want to do is we want to resolve the clouds, because then we need to make fewer approximations, and evidence has shown in recent years that this will also reduce uncertainties. But of course, these simulations are really expensive and will probably remain too expensive for a decade or two if we're thinking about long-term climate projections. But we now have the capability to run short-term high-resolution simulations. And now the basic idea is, well, can we use machine learning to basically provide a shortcut, learning from these short-term high-resolution simulations to improve our low-resolution climate models? So the basic idea then that I want to talk about goes like this. So if we think about our simplified model of how a climate model works, and we figured out that the physics, the parameterization of these subgroup processes is the main driver of uncertainty. We want to replace this with a machine learning model. And for this, we need to build a training data set. A training data set where for each state, so the conditions of the atmosphere, typically in one column, we know what the tendencies caused by the subgroup processes are. And we want to get this training data set from a short-term high-resolution simulation. So the idea is you run a few weeks or months or maybe even a few years of high-resolution simulation, and then you coarse grain and build this training data set, train a machine learning model, plug it back into your climate model, and then hopefully get better forecasts. And so whether this will work, we'll examine in a minute or two. But before, I need to go back and talk about this step of coarse graining. So basically building the training data set from my high-resolution simulation, because it turns out that this is actually not that trivial. And I want to present 4 different ways of doing this. The first one is the one that we took, and it's kind of cheating because it's not actually using a 3-dimensional cloud zone simulation. It's using what's called a super parameterized climate model, where instead of a traditional cloud parameterization, you have a little two-dimensional cloud resolving model in each grid box of the climate model. And then the great thing about this is that this is an exactly defined problem. You know exactly what goes into your cloud resolving model, you know exactly what comes out, and now your job is just to emulate this. Problem, of course, is it's not really the real deal. We would like to approximate three-dimensional cloud resolving models. Now here the problem becomes harder, because now it's not clear anymore after the course. So you have to do some course grading. You have to find out, in my eventual lower resolution simulation, what will be subgrid and what will still be resolved, because you only want to emulate with a machine learning model what will be subgrid. So you need to somehow figure that out. You need to separate the tendencies. One way is doing this sort of approximately. The idea here essentially is you compute a coarse grained advection term, you compute the residual at every point, and that is what is subgrid. And if you want to find out more about this, this is the reference here, these papers. The great thing is this is model agnostic, but it turns out that this is kind of sensitive because you're doing finite differencing in space and time, and so it's kind of sensitive to the time step. And also, these residuals that come out of this are kind of noisy and do not follow any physical conservation laws. So another approach that has been explored in this paper is, well, can we do this exact? And you can, with some caveats. The idea here is you run the same model in a low resolution version and a high resolution version. You start them with the same initial conditions. You run them for one time step, and then after one time step, you basically check what is the difference. And that will be an exact difference between your two model versions. The great thing is, because both the low resolution version and the high resolution version follow physical constraints, so will the difference between the two. So it's a more constrained problem in a physical sense. But there are some limitations. So this is yet to be tested for long time steps and applied to real models. So this is still only a proof of concept. Now, learning from three-dimensional cloud resolving models is great, but what we really want to get closer to observations. And so one approach for this just came out beginning of this year. The idea here is you run a training simulation where you nudge your model towards a reanalysis, so an observational reanalysis data set. And then your machine learning goal becomes to learn the nudging tendency. This is great because you actually learn the observations, and also it's kind of an easier machine learning task, because rather than trying to replace a parameterization, you're really just trying to learn a correction term. Again, these tendencies can turn out to be pretty noisy and do not follow any physical conservation properties, and this might lead to problems that we'll encounter in a slide or two. So these are four approaches for creating this training data set, and let's now just briefly look at some results, because a lot of the results, a lot of these studies have quite a lot in common in terms of the results. So it kind of works, and this is just a visual illustration of this. So on the left here, you see high resolution simulation. This is run on an aqua planet. This is why it doesn't really look realistic. This is water vapor, essentially. And then if you run the model in a lower resolution version, you can see that it looks structurally different. But then applying a machine learning correction term or parameterization, you basically recover the structure from the high resolution version. So this is great, and this is really kind of an interesting result. One really cool result is from this last approach that I talked about, the nudging approach. And they tested their model in a weather forecasting mode, and they basically get a lower forecast error when they apply their machine learning correction. And this is really cool. Now, what all of these studies have in common so far is that they are working with a pretty simplified setup. So most of the studies on the previous slide are looking at an aqua planet with a reduced set of physical parameters. This nudging approach actually looks at a realistic Earth, but also at very coarse resolution, so much coarser than what you would run an operational weather or climate forecasting model. And despite all these simplifications, we still have some pretty strong problems. And so one thing that can happen, and which is illustrated in this little animation here from our study, is that you can basically get model crashes. So what will happen is that at an individual grid point, the output of your machine learning algorithm, in this case a neural network, will become increasingly unrealistic and essentially lead the model to crash. Now, even if this doesn't happen, what we see often is we see large biases. So this is again from the nudging approach that I talked about in the previous slide that had such good weather forecasting results. If you run this approach now for longer times and compute a mean climate bias, you can see that it has huge biases on the order of tens of degrees Kelvin. Now, the main point of my talk, which I'll make in the next slide, is that we do not currently have a principled way of fixing these issues. And I call this issue the optimization dichotomy. So a dichotomy is a really strong contrast between 2 points. So the contrast is essentially between what are we optimizing for? We're optimizing, we're building this training data set. We're training a machine learning model to map from state to tendency. This is what we're optimizing for. What we actually want is, well, we want better weather and climate forecasts. So better weather forecast is a better forecast after a few days, lower RMSE error or something like that. A better climate forecast is a forecast that, if you look at statistics, better matches observational statistics. And the key problem here is that there's a huge gap between what are we optimizing for and what do we actually want. And then specifically that gap are thousands, if not millions of time steps in which the machine learning model has to interact with all of the other model components, so the dynamics or any other physical model component. It has to interact with itself through many time steps, and simply hoping that a machine learning model that has been trained on this single time step mapping will also perform well when you then run it for long time steps and will do what you actually want it to do is kind of wishful thinking. Now, it's interesting to draw an analogy here to traditional parameterization development, which is based on physical expertise. So, if you build a traditional parameterization, you plug it into your model, it probably also doesn't do what you want. The difference here is that you have a number of physically meaningful tuning parameters where, based on experience, if I change this parameter a certain way, it will have this effect. And so you can use this intuition to tune the model to do what you want. You cannot do this with machine learning models because, for example, the neural network that we use had 500,000 parameters. They're all physically meaningless. We're not going to start tuning those. So before I talk about potential solutions to this problem, I want to put this into context of machine learning parameterization, because what I'm specifically talking about is improving models by learning from high-resolution simulations or observations. This is a really difficult task, as we've seen just now. Now, you can build machine learning parameterizations with a slightly different setup. So there are cases where you have a really good parameterization, but it's just really expensive. So for example, radiation is a classical example. We can run very accurate radiative transfer solvers, but they're very expensive. The idea here is basically you run this expensive parameterization, build a training data set from that, and then learn a machine learning emulator that tries to do exactly what this other parameterization does. This is an easier task because you can hope that by building a large enough training data set, you have a really constrained problem, and if you cover the entire phase space of what you also want to then simulate with your training data set, then your hope is that you will not run into the problems that I talked about in the previous slide. So radiation is a classic example, microphysics, gravity waves. There have been some really interesting studies there recently. Now, we want to think about improving models because the problem is for convection, for clouds, we tend to not have good parameterizations. We don't have good expensive parameterizations. We just don't have any good parameterizations at all. So we need to find these, and the idea is using high resolution simulations for that. But we've seen that here coarse graining can be an issue. Simulations tend to struggle with biases and crashes. And high resolution, of course, while it might be better, is still not what we actually want. What we actually want is getting closer to observations. Here we've seen this nudging approach, but again, this, as I've mentioned in the previous slide, does not optimize for what we actually want and runs into similar problems as the other approaches. So how can we do better? There are two sort of broad classes of approaches here, and first is based on differentiable physics. The idea here is that instead of optimizing only for one time step, you run a longer simulation and optimize through the simulation. Then you can optimize directly for an RMSE against observations. This requires a fully differentiable model, which we typically don't have, even though there's an interesting analogy to 4D bar, which is a data simulation algorithm, which is only typically used for estimating the initial state rather than the model parameters, but there might be some synergies here. There's this paper by Alan Gear that lays this out quite nicely. If you don't want to deal with differentiable models, you can use a gradient-free approach. And I will not talk a lot about this because I know there are 2 talks by people from the Climate project, which are pursuing this approach. So I'll leave it for the sake of time. Final slide. Big picture comments on hybrid machine learning physics modeling. So neural networks are very capable function approximators, which essentially means that theoretically there's a huge potential for speeding up or improving complex simulations. Now, there most likely exists a neural network that will create a better weather or climate simulation. The problem is just how do you find it? Because neural networks are only good at exactly what they're trained for. They can interpolate quite well, but they cannot extrapolate. The main point of my talk here is that currently we're not training neural networks for what we actually want them to do. A key takeaway from this is that if you train a machine learning parameterization offline skill, so how well does your neural network learn the training data set, is not indicative at all of how well your neural network will perform online when you plug it back into your climate or weather model and evaluate your longer term simulation. The challenge then becomes, how do you train a neural network so that it actually optimizes for what you want? The idea here is you need to somehow train the neural network within the coupled system rather than separately. So this is basically my talk. I just want to advertise one thing. So we're all here because we find this machine learning very exciting for climate and weather research. And there are a lot of papers being published, a lot of data sets. And so what we notice is essentially that there doesn't seem to be a website where, there's just a list of all the available data sets for some pre-processed data sets or so. So we created one. It's at mldata.pangeo.io. So you can go there and you can see a list of pre-processed data sets specifically for machine learning use. And if you have a data set yourself or you know one that isn't on there, you can also add it easily. So that's just sort of a final advertisement. So thanks for listening.